is quite useful. We found a more advanced zero-knowledge proof with more requirements is needed. Actually, there are problems in traditional zero-knowledge proofs. The first problem is that most zero-knowledge proofs are interactive protocols. The prover has to prove in something after many rounds of communication with the verifier. Like in the Alibaba cave, we have to do n times the whole process, and every time Bob will claim in which path Alice should goes out. And this is very expensive in practice for communication bandwidth, especially in distributed settings like blockchain, because uh, blockchain is a public system and everybody can join and leave. So there are large number of people are verifying zero-knowledge proofs. If the zero-knowledge proof is interactive, there are many communications between the participants to with the blockchain, and this is very expensive in communication. The second problem is that the proof size is too large. Since the blockchain is growing and more blocks are appended, and more participants are joining the system to do the consensus process and appending new blocks. If the proof size is too large, it will lead to the blockchain size explosion, and clients may not be able to download and store it, which makes the system not scalable. The last problem is that not all zero-knowledge proof can be verified by everyone. Some zero-knowledge proof can be only verified by designated verifier. If so, such zero-knowledge proofs won't be compatible with the blockchain's public ledger concept. Therefore, we need a new kind of zero-knowledge proof that not only satisfy the completeness zero-knowledge property and the proof of knowledge properties that we have mentioned, but also such a zero-knowledge proof protocol must satisfy three new following properties. The first one is called non-interactive. That means the prover only sends one message to verifier, and there's no interaction between them. The second one is called succinctness, means that the proof size should be very short. Ideally, how short is short? Ideally, the size should be independent of the size of the function f. The third property is called publicly verifiable, means that everyone in the system should be able to verify the proof without any secrets. So here I give a conclusion of the 6 properties we should need, and we call a zero-knowledge proof that satisfies these 6 properties together is called ZK SNARKs. After giving you a very basic introduction and intuition about what is zero-knowledge proof and what is ZK SNARKs, I would like to introduce the current status of the ZK SNARKs research and how we choose our ZK SNARK candidate to be used for our Zend network. Recently, research about ZK SNARK is full-fledged, and there are a bunch of different ZK SNARK constructions that were concluded in this figure. Basically, ZK SNARKs can be based on 4 different cryptographic assumptions. The first one is collision-resistant hash function. ZK SNARKs based on this assumption is usually quantum-resistant, since it is based on collision-resistant hash function, which is a symmetric primitive, and such primitive is usually lightweight in computation. The second assumption is the elliptic curve-based discrete log assumption. The most representative one is bullet proof, which is a well-known range proof protocol used developed by Bonnet et al. Um, Knowledge of exponent assumption and groups of unknown order are kind of new assumptions proposed in recent years, and many advanced ZK SNARKs are proposed based on them. um, Basically, in this talk, I don't want to discuss each of construction in details. Here, I just would like to let you know that we finally choose um, Sonic, Merlin, and Plonk as three potential candidates for our Zen network after comparing measures listed in the link. And if people are interested in what's the time complexity of each of them is, I have concluded each measure in this list. Here in this talk, I just give a conclusion that we have chosen Sonic, Marlin, and Plonk as the final three winners of the potential candidates. Basically, the reason we choose these three candidates is because they have the following advantages. The first one is that all of these constructions have a unified approach to construct. Basically, uh, all all of the these three constructions are based on a new crypto primitive called polynomial commitment. The unified approach, roughly speaking, can be concluded that we can first represent the function as an arithmetic circuit and convert the circuit description into a polynomial. And then we run the polynomial commitment to build an argument to prove something about the polynomial. And finally, we can add on other features generically if depending on what we need in our construction and in our applications. So a unified approach allows us easily plugging in different crypto building blocks if we require new features instead of uh, creating a new construction that is independent of this line of research. The second advantage is they have better efficiency than any other ZK SNARKs in practice. In particular, they have efficient proving time and proof verification is super fast because the proof size is very short. Actually, three of them can achieve constant size proof, which means the proof size is totally independent of the function size f. Uh, Having better efficiency is important when they are applied in blockchain. We cannot, because we cannot tolerate a very long proof generation time and a very large proof size posed on blockchain. The third advantage is that these constructions are flexible in different applications. This is because they achieved an advanced but unique term called universal function. That means the function f can be applied in different applications. Zero knowledge proof is usually defined for a specific MP language, which is defined by a specific function. Universal function allows prover proving different MP languages using such a universal function, such that we can launch it one time and use in different settings and many times. Finally, I would like to give in a benchmark comparison we tested using the corresponding open source implementations of them. Our goal is to choose a final candidate among Sonic, Marlin, and Plonk. Also, another goal is to compare these three candidates with our existing zero-knowledge proofs method, including ring signature-based NISC and ZK SNARKs. Note that these numbers are just ballpark numbers, but it's enough for us to choose the candidate which is useful for us. We have tested Sonic, Marlin, and Plonk with 2 to the 18 gate circuit, which is large enough and reasonable. The ZK SNARKs is tested with 256 leaf Merkle hash tree. From the comparison, we can conclude the following results. The first one is that we know that Plonk has better proving time than Sonic and Marlin, and also Plonk has the second result is that Sonic, Marlin, and Plonk all have very fast verification time and short proof size than ring signature based NISC and ZK SNARKs. And comparing the proving time of Sonic, Marlin, and Plonk with ring signature based NISC and ZK SNARKs, the proving time is still a bit large because the ring signature based NISC proving time is just 17 milliseconds, and this is for example, Plonk has 14 seconds proving time is a bit large in practice, I think. So we are still working on trying to some new methods to reduce the proving time from 40 minutes to 7 minutes, but these methods need to sacrifice a bit about verification time, and we are still finding a good trade-off to improve proving time, but sacrifice not too much on verification time. And the final result we conclude is the Sonic, Marlin, and Plonk. That's not a result. It's an open fact that Sonic, Marlin, and Plonk have to launch a secret one-time setup, but the ring signature NISC and the ZK SNARKs are transparent, that we have mentioned in the picture. Here I have to say, getting rid of the secret setup is an open problem in the research community. A lot of research works are working on getting rid of it, but there are many trade-offs that sacrifices other measures, especially improving time and verification time. So right now we don't have very practical trade-off, practical constructions that can find a good trade-off between getting rid of secret setup and efficient proving and short proof size. And but recently there are some progress in theory that ZK SNARKs can have they claim fastest proving time, and they claim is much better than the measure I have mentioned, it which takes 2000 seconds. We are still following up what the new method is after maybe after the stock is open sourced totally. So that's all I